In this video, we're going to start talking about polarized light. Now, when you have a light wave, remember that a light wave is a combination of electric and magnetic fields. Well, we've always drawn the electric fields as if they were vertically oriented, kind of like this. But that's not always the case. Sometimes the electric fields might be oriented horizontally like this, or maybe at some angle in between. Doesn't matter. And most light that exists, most of the light we see out in our atmosphere, for example, is non-polarized light, meaning it's any direction at all. But if we start singling out a single direction, like if we say that light is only, the electric fields are only oriented vertically, then we start saying that that light is polarized. Now, there's some fun things that we can do with polarization. I want you to consider this light as if it were a wave in a rope. You have this wave in a rope, and currently it's vertically polarized, meaning the electric fields are just oscillating vertically up and down. And then you put this sheet, this box with a hole in it, in the path, and we're going to orient this hole so that it is vertically lengthwise, so that the opening is kind of a rectangle that is oriented vertically. Then when you have this vertically oriented wave, it can pass straight through that gap, not interfered at all. That gap won't cause a single problem. However, if you have a horizontally oriented or horizontally polarized wave, then that's going side to side. Then when it hits this vertically oriented gap, it runs into the gap and into the sides of the gap, and it kills the wave, and you get no wave at all on the other side. So the idea of a polarizing filter is a filter that will allow one polarized direction of light to pass through, but will block out the opposite, the 90 degree, the one that's the orientation that's perpendicular to the one that it let through. So in this case, we have a vertical polarizing filter that allows the vertical waves to pass through, but cuts out all the horizontal waves. Now, with light, we can do the same thing, but instead of using gaps and slits and things like that to let the light through, we use a chemical. We have a filter that is covered with a chemical. That chemical interacts with light in such a way that it will only allow vertically polarized light, but block horizontally polarized light, or vice versa, whatever you'd want. Now, when you have unpolarized light that passes through the polarizing filter, then only the component parallel to the filter is transmitted. Let me see if I can describe this way. You have light that is unpolarized, meaning you have light that's going in any direction at all. Now let's put in a filter here that is only vertically, it's a vertical polarizing filter. Then after the light passes through, you are only going to have the vertical component of that polarized light. Now, if we have some initial intensity here, then the intensity of the now polarized light would actually become 1/2 of your initial intensity. That's because all of the vertically polarized light is let through, none of the horizontal is let through, and then any that are at an angle, the vertical component is allowed through. It turns out that on average, half of the light has a vertical component to it. And so the intensity is cut in half because only half of the light comes through. Now, what if the light is already polarized? Let me back up for just a second. This figure down here actually really well describes what I was just talking about. If you have light that is polarized at some angle, then you just take the vertical component of that, and that comes through where any horizontal component is cut out. And so it only allows the vertical component to be transmitted. So if your original light was unpolarized, then the new intensity is going to be half of what it was originally. But if the incoming light is already polarized, then you can find the new intensity following Malus' law, which states that its new intensity is going to be whatever the initial intensity was of the previously polarized light times the cosine squared of the angle between the polarized light and the filter. So in this case, your polarized light had an angle that looked like this. You have a vertical filter, and so that would be your angle theta right there. So this is kind of creates an interesting phenomenon here. Let's say you have unpolarized light. It hits a vertically oriented polarizing filter. So only the vertical components are allowed through. So you now have plane polarized light oriented vertically. You put in a second filter down here, but this time you orient it horizontally. Well, it only allows the horizontal component to pass through. But your light is vertically polarized, which means there is no horizontal component. Therefore, since there's no horizontal component, no light can actually pass through. You can try this. If you have a couple pairs of polarized sunglasses, you can put the two lenses together and turn them until the light disappears. It actually makes everything go completely black. It doesn't let any light through at all. And then you can tilt them back and it will actually let light through again. So that's pretty cool. But now is where it gets strange. So you have your two filters, one vertically polarized, which polarizes the light vertically, and then a horizontal filter, which will then block all the light. What would happen if I place a third filter in the middle, oriented at 45 degrees? Well, let's say that here I have some intensity I naught. Then here I'm going to have vertically polarized light at some intensity I1, which follows I1 would equal I naught times the cosine squared of 45 degrees, which is 1/2. Cosine of 45 is square root of 2 over 2. Cosine squared then would be the square of that, so 2 over 4, or 1/2. Like so. Excuse me. You know what? That's if it's polarized light. We're dealing with unpolarized light. Well, we get the same result anyway. So I1 is going to equal 1/2 of I naught because you're going from unpolarized light to polarized light. But then this polarized light, which is oriented vertically, comes and hits a filter that is 45 degrees from it, and thus polarizes your light at that 45-degree angle. Now you have some intensity I2, which now we do need to follow Malus' law, which states that I2 is now going to equal I1 times the cosine squared of 45 degrees, which cosine squared of 45 degrees would be 1/2 times I1. I1 is 1/2 I naught, so that becomes 1/4 of I naught. Half of a half would be a quarter. Now here's the interesting thing. Now you have light polarized at 45 degrees. And it hits this horizontal filter, making a 45-degree angle between the light and the filter itself at some intensity I3. So now we've got horizontally polarized light at some intensity I3, which would be I2 times the cosine squared of 45 degrees. Cosine squared is 1/2 of I2, but I2 was 1/4 of I0, so half of 1/4 would be 1/8 I0. But wait a second. Back in this situation here, we got no light at all. But now all of a sudden, it's the same situation, but just with a third filter in between the two, you do actually get light coming out of that, just as we calculated here. How is that possible? Well, remember that a polarized filter only allows the component parallel to the filter itself to pass through. So going from the vertical to the 45 filter, it was vertical, but there is a component of that vertically oriented light that is parallel to the 45-degree filter. We found that, passed through, and you just pulled out that component that was parallel to the filter. But now that polarized light is at a 45-degree angle, as it jumps to the horizontal filter, there's now a component to that light that is parallel to the horizontal filter. And so it allows light to pass through. Really interesting little phenomenon that happens there. Now, so you can use filters to polarize light, but there is a polarizing filter that happens in nature. One of the best polarizing filters that is out in nature is reflection. As light comes down and hits the ground, hits asphalt is a great polarizer. Water is a great polarizer. It hits we'll take the water, light hits the surface of the water and reflects upwards. Because of the chemicals of water, the water molecule, it takes some of that previously unpolarized light and it polarizes it so that horizontally oriented light waves are allowed to be reflected, and only some vertically oriented light is allowed through. But at a special angle, which we call the Brewster's angle, that polarization becomes 100% effective, meaning only the horizontally polarized light is reflected. And we can find that angle by using the tangent of Brewster's angle, theta p. It's going to equal n2 divided by n1, where n2 would be the index of refraction of the reflecting surface, and n1 would be the index of refraction of the incident angle. This is why when you're driving around or you're out in the water or something, it's nice to have polarized sunglasses. Polarized sunglasses are made so that they're oriented vertically, they block out any horizontally polarized light. And thus, polarized sunglasses will completely block the light that's been reflected from the surface of the water or the surface of the road, and thus makes it so that any glare from the reflection is eliminated, makes it so you can see better.